Do you see my presentation now? That's good. Okay, so as was mentioned, my name is Antti Häkkinen. I come from LUT University in Finland. I work here as a professor of solid liquid separation technology. And what I'm going to introduce to you now is a project that we just finished at the end of last year. We did work on the project almost for 4 years, or 3.5. And now I have 10 minutes time to tell about the project, so it will be very challenging. So I will only say you some of the main points of what we did, and then if you are interested, there is much more information available in the internet, and I can of course send you more information by email if you want. But yeah, this project doesn't actually have too much to do with the with soil or with water. It is mostly about utilization of industrial side streams. So it started about 4 years ago when we started having discussions with our local industry. You can see here a map of Finland in here, and the red area is the South Karelia where we are located, and all of the partners in this project were coming from this area. So we have here industry, pulp and paper industry, also mining industry, and we have several our university as one of the participants, and then we had University of Applied Sciences, which is located very close to us also. Then in the project we also had a small company from our neighboring city Imatra. The company is called Fimatech, and they are specialized in producing 3D printers for printing these quite large building elements. And then we also had 2 design companies called Total Design and Total Reform, which were designing some new structures based on the materials and methods that we were developing in the project. The project was funded by European Commission, and the overall budget was about 4 million euros. And the main coordinator of the project was Lappeenranta City. So it was funded from a program called Urban Innovative Actions, which is open only for cities. So any company or university cannot apply funding from there. It has to be applied by the cities. So we started thinking about the side streams that we have here in this area, and here you see our original idea. So on the left-hand side here, we have the industry. So UPM is a large pulp and paper company. Nordkalk is a local mine here in Lappeenranta. Stora Enso is also a pulp and paper company, as is also Metsä. Outotec is a fairly large technology producer. So we collected information about different side streams that we have here. Those include very different kinds of ashes coming mostly from pulp and paper industry. Then we had green liquid wrecks, we had mine tailings, we had construction and demolition waste, we had some fiber waste and materials like this. So the industry was providing the materials to us. We were then analyzing the university, the physical and chemical properties of these materials. And then there was another partner, a small company, where they had a specialist in chemistry, who then developed some recipes which we can use for making kind of a synthetic stone. So we are talking about geopolymer composites. So, and the idea was that we could replace some of the concrete nowadays used with this geopolymer composite. And the main motivation for that is that in the cement industry is producing about 8% of all the carbon dioxide emissions in the world. And if we can reduce that number, that is of course would be a very good thing. And we thought that it will be possible by using these geopolymer composites. Then after the material recipes had been made, the information and raw materials were delivered to this company, Fimatech, which then 3D printed some pilot elements. This picture shows here noise barrier, skate ramp, and a park bench. These were just some examples what we were thinking about. And at the moment we have built 100 meters of noise barrier close to Lappeenranta by using these materials. You will see an example of that later on. Then on the right-hand side of the picture, you can see that we also, a big part of our study was also life cycle analysis to really get some real information about the environmental impacts of these materials compared to normal concrete materials. And then also different kinds of business models were studied, because of course in here the waste of one company will be the raw material of another company, and that is that means that the original raw material may in some cases have even a negative value. So it is creating very different kinds of business models how we can operate. Okay, further on, you can see here the structure of the project. I will mostly be talking about work package 4, but that was the part where we collected these different side streams, analyzed those side streams, and then developed these material recipes. Then in work package 5 and work package 8, those were mostly like scale-up work packages. So there we scaled up the pre-treatment techniques and also did some investments regarding the 3D printing technique. In work package 6, we did some pilot elements, which are still, the work is still continuing even if the project already ended, but that was mostly for building the pilot elements here in the city. And then work package 7 was focused on these circular economy and sustainability assessment issues, including both the life cycle analysis and the business models. So this was the overall structure of the project. Here you can see the main idea. So we have different side streams, and now the analogy between these geopolymer composites and concretes is kind of shown in here. If we talk about concrete, we need water, we need cement, and we need some fillers, normally sand. And in the case of geopolymer composites, we are not using too much water, but we are using some very alkalic solutions, which are called alkali activators. They can be sodium silicate or sodium hydroxide or anything like that. Then we have some binding material. We can use commercial materials such as metakaolin, but in our project we were trying to find suitable materials that have the suitable chemistry, and they can be used as the binding material. Very crucial parts here are the concentrations of aluminum and silicon, but if we have suitable concentrations of them, they can then react together to create these geopolymer structures which are very strong. And then we also added, of course, some aggregates which replaced the normal sand in the concrete. So in our case, these aggregates were mostly some ash samples, but mainly the tailings from the mining industry. Time is running out. Just to show you quickly a list of samples that we collected. So we had 24 different samples. Most of them are from this local area close to Lappeenranta. So the samples are ashes, vinegar dregs, tailings, and so on, what I already explained. And then in our work package, we analyzed these very carefully with different techniques. Here you can see a list of maybe 12 different techniques. So we got a full characterization information about these materials, which were then this information was then utilized by this company called Apila for making these geopolymer recipes. Here is just one example of the results that we got. We studied the dissolution of these different materials in different kinds of solutions, and this is important because that defines the amount of reactive elements in our solution. The reactive elements that can then create these geopolymers. So we tested different solutions, different temperatures, different leaching times, and so on. Just a very quick example. And then in here we can see the structures of 5 different recipes. I know the text is very small, but I will distribute the slides later on. As a reference material, we had normal concrete, and then the recipes 1 to 5 contain different kinds of industrial wastes and in different amounts. And I have to highlight that here in the recipe number 4, the amount of industrial side streams was about 99.5%. So it is almost completely waste, and you can see that it looks exactly like concrete. And we also tested the hardness values of these, and they were similar to normal concrete. So we should not have any difficulties with that. Then very quickly, I show you a video now. This is showing the 3D printing of these kind of elements which we made for building the noise barrier. And you can see that these elements are kind of curved to all directions. So this was made intentionally because we wanted to show that with the 3D printing we can make shapes that are not possible to that cannot be done with the normal casting techniques. So here you see the extrusion part. So it's basically an XYZ table, and it is extruding the concrete mass or the geopolymer mass and running it layer by layer. So it's very important to optimize the structure of the material in such a way that it hardens quickly enough that if it hardens too quickly, it will block all the pipes. But it's kind of an optimization problem. But here you see our current system that we use for making these building elements. And here you finally see those building elements installed next to the railway where we have this noise barrier. So on the right-hand side, you can see elements which have been made by casting, by using these different new materials. And then we had these elements which were made by 3D printing, now partly installed there. So it is a 100-meter barrier, and we will be following how it survives in very Arctic conditions, how the temperature changes and humidity changes will affect on the material. I think I'm running out of time now. Here, quickly showing the life cycle analysis for these 5 different recipes. The R0 is the normal concrete, and then here are the 5 different geopolymer composites. With the first one, where we had some commercial materials, the life cycle or the amount of CO2 emissions was higher than with the concrete. But here is the extreme case where we had 99.5% of side streams, and we can see that there is a huge difference in the global warming potential between this one and the reference case. So we can conclude that these materials can be used for successfully decreasing the CO2 emissions. I would have another video in here, but I will skip that. And I will leave you with this. There is the web page of our project where you can find much more information, and you can always contact me if needed. Sorry for exceeding the time, but thank you very much.